Hello everyone, welcome to my channel PhysicsBro, and we are going to discuss about electrostatic potential. So we know that there is something called electric field. Okay, there is something electric field, and we can calculate it by using two methods. What is that? One is Coulomb's law, and another is Gauss theorem. Okay, Gauss theorem. So Coulomb's law for every body, every symmetric or not, it doesn't matter, but Coulomb's law is applicable, and Gauss theorem is applicable for everything, but you cannot calculate everything. Symmetric bodies, for symmetric bodies you will apply Gauss theorem. Okay, so this is the electric field, and this electric field is the sole part of the theory, but we need something that's called electrostatic potential. But why? You must know that why we need it. Okay, why electrostatic potential? That's a very important idea, electrostatic potential. First of all, this potential and the potential energy is different. Okay, electrostatic potential, this potential does not mean that potential energy. Be careful about that. Okay, so why this electrostatic potential? First of all, that look, electric field is a vector quantity. This is a vector quantity, so if you have to treat with it, you have to be very careful. It is a vector, so you must be very careful because there is a direction, and you have to add the directions to when we will add some electric field. But if we have any scalar function, say phi, if scalar function, we can just replace electric field by some scalar function, then I think this will be very easy to understand, because scalars just add, they don't have any direction. So that's why electrostatic potential comes. But we must have some rules, you know, you must have some rules. What will be the rules, and why you can use it? Okay, there is a special property of electric field, that is curl of E equal to 0. So this is a conservative field. Conservative. If any conservative field, there is an conservative field, say A, there is a very important and very crucial vector identity, that if there is a conservative field, there conservative vector, and you can write it like this, then you can define another potential, you can define a scalar function for A. Okay, so mathematically you can write A as some gradient of phi. Okay, that's the idea. So look, electric field satisfies this idea. So electric field can be replaced by this thing, this scalar thing, and scientists thought that okay, let's do it, and they replaced electric field by some mathematical expression of grad phi. So this is the basic and the most important idea of the electric field. Okay, so electric field can be replaced by phi if you can calculate phi, and phi calculation is easy. Phi calculation, that is potential calculation, is easy. Potential calculation is easy. It is easy. So if you can calculate phi and you do this thing, that is called some gradient, and you will get the electric field. So let's have some idea about the electric field and electrostatic potential. Physically possible or not, but we are just here for calculation of electric field from phi. So E equals to, by definition, it is grad phi, and how will calculate grad phi? Minus is there, okay, but grad, the definition of grad is like this: I cap plus del by del y j cap plus del by del z of k cap. Okay, and there is a phi. So this whole thing is called the gradient. So we will just operate it like very simple operation, del phi by del x and I cap plus del phi by del y and j cap plus del phi by del z and k cap. Okay, look, when we'll do this thing, this is called partial derivative, and the partial derivative says us that when you will when you will calculate it like that, when you will differentiate it, there will is only one variable, say x. In this case only x, it is not d by dx. D by dx called whole derivative, but it is not a whole, it is a partial. So in case of partial, you will put all other y, z or etc. constant, and only variable is x. So the derivative says minus, this says y, z only, because x and there is x. Okay, you're off, I cap plus. And what about this? In this case y will be eliminated and there comes x, z, j cap plus and x, y and k cap. So this is our electric field. So if it is a scalar function, it is a scalar, then you can easily do it, easily, very easy, is not it? Okay, so what we have found that there is some mathematical description about. So what we have found that there is some mathematical description, like vector E has some property that curl E is 0 and E can be replaced by minus of grad phi. But what does it really mean? This is a mathematical idea, so we need some physical ideas too. Okay, so let's have some figure, because we need it to understand some physics. So there is a charge, say Q, and there is another point P. Okay, somewhere in the space, somewhere in the vacuum, you say there is a point P. So you can calculate the electric field by directly if you know the R. This Q is called the source charge. Remember, this is a source. This is the source of electric field. Okay, and there is some test charge. Here we come some test charge, or this called a field point, test charge, and this point is called field point. Okay, so are you clear? That remember that source and field, this idea must be clear for every problem. If you forgot about source and field, and if you mixed up, then the problem will be very much disturbing. Okay, now this is source. So source have some field. Can you calculate it? Okay, I can calculate it easily. So what will be the what will be the field? So field, we can write it like E. Okay, this is our field. Now let's have the idea that if we have any charge Q. Okay, I'm doing here the more clear picture. So this is a Q and there is a charge small q, and we try to bring it from point B to some point A. So we are going from B to A. So the charge is moving from B to A against the source, against the field of the source, force of the source, anything you can say, but against the influence of the source. So I am writing here that charge Q is moving from B to A against, I am writing against the influence of source, So there must be some work done, because this field, this source will not allow you to bring the Q easily, is that it? So there must be some force that will resist it. So there is some force. The force is Q into E. Okay, this is just Coulomb's law. Don't be scared about this formula, but this is just Coulomb's law. Okay, it is a sophisticated way to write Coulomb's law. So if this is the force on Q, then what will be work done? Okay, there comes the work done. So work done equals to, we know it, F dot dr, F dot dr. Okay, and from B to A. Okay, and look, if we choose some point here origin, then this portion is positive direction and this is negative direction, and the whole thing, that is the charge q, small q, coming from somewhere positive to somewhere negative. Is that it? Look, it is more positive, B is more positive than A is also positive, but B is more positive, so we have to take some negative to balance the idea that we are moving through this dr. Dr is actually, dr is negative here. If you choose some small element dr, get the idea, get the physics first. So this is decreasing, this is not increasing. So if it is decreasing, then we can put a minus sign. Is it clear why we do it, this there is minus? This is the cause that if dr is decreasing, then we are putting a minus here. Okay, so this is our work done. So if it is then our work done, then can we write it something like with Coulomb's law? Okay, we can write it minus q into integration of B to A, I think B to A, and F dot dr means q E is here and dot dr. Okay, so q is a fixed one, q is a fixed one, so we can write it like this. So work done W from B to A, I am writing B to A. This is just a notation that the body is moving from B to A, and this is minus q into B by A and E dot dr. Okay, now WB from A, this is equals to, I am writing it again, that q into E dot dr from B to A. But look, this work done depends on q. Okay, work done depends on the test, work done depends upon the small q. Okay, this E is generated for q. Remember that this E, this electric field is generated from q, the source, and this q is our field point charge or any charge maybe. So work done depends upon q, and we will do something interesting, that we will eliminate this q. Why? Because we want some independent thing, the q independent thing. So what we can make? We make WB from A by q and minus of B by A into E dot dr, B from A and E dot dr. Look at this point. Now if there is any charge put here, this is only source. Look, this depends only on source. Okay, so there is no need to think about which charge is coming and which charge is going. No, that's not in need now. We only care about the source, and it is easy to calculate because we don't have to mix up the q and small q and capital Q. Okay, so this is the term we define as the potential phi. Okay, so potential phi is work done per unit charge or per charge, any charge. So if say and the unit first, so work done is joule and the charge is coulomb. Okay, so let's explain the joule per coulomb means. Actually, say a charge of 5 coulomb is coming from somewhere, and we are here, and we measure that if we move this charge and from somewhere to this point, let's say it's coming from somewhere to this point, and we need 100 joule of work done, 100 joule of work done to bring the charge from somewhere to this point, say A point. It is coming from some point B and it is here in A point A, and we need 100 joule of work. Okay, so the potential says that okay, it's for 5 coulomb, so per unit charge there is 1 coulomb, it needs only 20 joule per coulomb. Okay, that is 20 joule per coulomb per coulomb potential is needed now. So potential is needed now from 20 joule per coulomb. So let's have the definition the book has provided us. Let's integration minus b to a and E dot dr. So this is actually not potential. Okay, what? This is not potential? No, this is potential difference. Okay, now there comes the potential difference. Why I am talking about this difference? Because the points are fixed. So this is B point or this is A point. Okay, so the potential in this point is say phi A and this is phi B, and this integration gives us phi A minus phi B. Okay, this gives us only phi A, phi B. So what will be the phi A and phi B? For this reason, we will extend the idea that, say, there is a source charge Q and some charge is coming from infinity to some point A. Some point A. So, what will be the lower limit? Lower limit is infinity. Okay. So, phi A is defined as minus of infinity to A and E dot dr. Okay, when you are talking about the from infinity to A, you are coming from infinity to A. Okay, you are coming from infinity to A some point, and what will be the phi B? Phi B is equals to minus of infinity to B and E dot dr. So is it the definite potential? Can we say that this is the definite potential? No, this is not the definite one, because it depends only upon the coordinate you choose. Or what is the coordinate? You can say that, okay, I am not talking about infinity, I am talking about say 100 meter. So the result will be something different, but the idea is same. And the 100, if you choose this one, this upper limit, lower limit. So just when we will calculate the grad phi, then the constant term, there will be some constant term and it will be cancelled. So we are not interested about that. Now what happens here? If we get some difference, just in this form, if we can write it, it is a calculus, and this is a very interesting calculus. Phi A minus phi B. Let's give this idea and let's see if we can go back to this one. So what will be the idea? Phi A is minus of infinity to A and E dot dr minus, there is a minus and there is a minus, so there comes a plus, and infinity to B and E dot dr. Okay, so we can write it this thing in a different form, that if there is a minus, then we can change the limits. How? The upper limits goes to the lower and lower limit goes to the upper one, A to infinity and E dot dr plus there comes infinity to B and E dot dr. Okay, now look, this upper and this lower are same, so we can eliminate both and we will be this lower and this upper. So let's go to the next slide. So phi A minus phi B, phi A minus phi B equals to, so I'm writing it again, from A to infinity E dot dr and plus infinity to B and E dot dr. Okay, you got it. And now we can write this like B to A and E dot dr. Okay, the form is not same, but we can write it like that, minus B to A and E dot dr. So this is our potential difference that we called about. Okay, so this thing is like this. So what we have learned today is that potential and potential difference potential difference are not the same thing, are not the same thing. Okay, are not the same thing. Secondly, potential and potential energy. Potential energy. They are not same thing. They are not same thing. Okay. So we can calculate it easily, because if we can find E, then we can find E dot dr easily.